Welcome back. So, today we are going to start the new and the last topic of this particular course, that is stress in soil. So, stress in soil, when you want to understand, then you should know why and what situation you basically you need this concept. Suppose you are going to find out, or you are going to place one foundation or maybe any kind of structure on top of the soil. Okay. Now, at certain depth of soil, at certain distance from the center line of the loaded area. So, if you want to find out the stress, how much stress is getting developed due to the application of this structure or due to the placement of the structure on top of the soil, will be, I mean, if you want to find out that stress at soil, then basically you need to know few say theories, as well as the whatever we will be covering in this chapter, that will cover that part. Okay. So, it is very essential. That means, any kind of extra structure or any kind of additional say construction is going to happen on top of the soil. Because of that, whatever extra stress you are getting or you are accumulating at the soil at some depth, okay, below the ground surface. So, that can be analyzed by this process. Now, why you need that? Because suppose when you are placing the foundation or any kind of additional structure on top of the soil, basically you need to know whether your soil is really strong enough to take that much of stress, whatever is getting developed due to the placement of the structure, right. So, prior analysis is very much required, and then from the soil strength property, okay, you can think or you can see that, okay, my soil is good enough or the strong enough to take care of the additional stress which is coming on top of the soil. So, this is very essential when you are talking about any kind of foundation or any kind of say any say embankment, okay, or maybe slope. So, below that whatever stress will be getting developed, you need to know that. Okay. So, this is an early method. So, early method is to use 2:1 slope. So, basically the early method is says that you have any say block, foundation block or any kind of say structure. On top of that you are having say total weight say capital Q, and that load is getting transferred to the soil with a 2:1 slope. So, this is your 2:1 slope. Okay. So, now at base, basically at this level, say at some depth z below the bottom surface of the loaded area. Okay. So, you will be getting the stress which is getting developed QV. So, QV is simply is equal to Q, capital Q, divided by the total base area at this level. Okay. So, this was the early method when actually no methods or no analysis was there. So, at that time people used to consider this concept. Still people used to have or used to use this concept and for some say easy computation or maybe quick computation, basically people use this method. Okay. So, now this was the earlier method or the very early stage this method was developed. Now, others have proposed that instead of 2:1 slope, others have proposed that either this dispersion, this is nothing but your dispersion line, the dispersion line either is making 45 degree with the vertical or 30 degree with the vertical, right. So, now basically what you are getting, you are telling instead of 2:1 slope, your slope is different. So, where the slope is defined by this angle, the 30 degree angle or 45 degree angle with the vertical. So, now idea will be remaining same, the total stress, that is small QV at the base of the say at the base of the loaded area, this area will be capital Q divided by the area at that level. Okay. So, that will be remaining same, only the dispersion is different. So, dispersion, people are saying the dispersion could be 2:1 or could be 30° dispersion or 45° dispersion. So, whatever may be the case, you can find out the stress developed at any depth z below the ground surface by QV, right, small QV. Now, the pressure increase, because this is the increase in pressure, because soil will be already having some kind of stress, right. As you go deep and deep, basically at any level the soil will be having the stress, vertical stress is equal to gamma into z, that already it is there. So, there is no there is no addition or no kind of alteration in that part. Okay. So, if you consider any soil deposit at any depth below the ground surface, okay, you will be getting the vertical stress equal to gamma into z. Apart from that, if you put any structure for which some additional load is coming on top of the soil, okay, so that load is getting transferred to some depth of the soil, and that can be calculated as the additional pressure or the additional stress. Okay. So, therefore, the pressure increase QV at a depth z beneath the loaded area due to base load Q, whatever we have seen just now, is equal to QV is equal to Q divided by B plus Z into L plus Z. So, if it is, say depending on the dispersion, basically you will be getting this area. So, what is the B and L? B and L are the breadth and length at that level, right. So, now basically what we are talking about, B plus Z is the total. So, if you see from the top, so this is the loaded area at any depth z. So, this is your say B plus Z and L plus Z, okay, and on top of that you have, this will be your B, this will be your L. Okay. So, B and L will be the loaded area, and below that basically at any depth z, if you want to find out the pressure increase, the additional pressure Q, capital QV, then you can calculate by this formula, right. Now, these are very crude way, whether it is there is no, it depends on some thumb rule or depends on some experience, but more sophisticated elastic analysis is available nowadays. Okay. So, theory based on theory of elasticity. So, based on theory of elasticity, Boussinesq proposed some different expressions by which you can calculate this kind of stress under some loaded area. That load could be concentrated load, could be uniformly distributed load over a circular area, or could be a stripped load, right. So, for any kind of load you can find out the pressure increase at any depth, say z. Okay. Now, the Boussinesq method in 1885, Boussinesq proposed this method. So, Boussinesq equation considers a point load on the surface of a semi infinite, right. Semi infinite means it is infinite in two directions, right. So, semi infinite, homogeneous, okay, isotropic, weightless. Okay. So, we are not considering the weight of the soil. So, the soil medium is weightless, elastic half space. Okay. So, we are considering elastic half space. So, if this Boussinesq equation or the Boussinesq expression was developed based on these parameters, like first one is semi infinite, second one is homogeneous, third one is isotropic, fourth one is weightless and elastic half space. So, based on these parameters, okay, Boussinesq has proposed some equation, some expression for a point load. Expression means, so if you want to find out the pressure increase at any depth z, okay, below the surface where the point load is acting, you can find out from that expression. So, let us see how that expression looks like. So, basically this QV is nothing but the pressure increase. Now, you are considering one concentrated load Q, as I told you, okay, the point load, or the concentrated load, point load is acting Q. Now, along this is your z direction, this is your x direction, this is your y direction. Okay. So, now along z direction you are going to the deeper strata of the soil. Now, for that Q, if you want to find out the pressure increase at any point, say this point, which is defined by two coordinates, that is small r and small z. So, if you know small r and small z, that means this is the point load. I can find out the pressure increase just below the point load when small r equal to 0. If some small r is there also I can find out the stress, right. So, basically you need r and z to locate a point at which you want to find out the pressure increase, and that pressure increase QB is given by this expression 3Q by 2 pi z square into 1 by 1 plus r by z square to the power 5 by 2. Okay. So, this from this expression, so if you know r, that means if you know the location of that point at which you want to find out the stress increase or the pressure increase, right. So, that location of the point is defined by small r and z. So, if you know these two things and if you know what is the magnitude of the point load, you can find out the pressure increase at any depth z at any radial distance small r from the vertical axis. Okay. So, I mean anywhere you can find out. So, if you want to find out say state of stress or the pressure increase here, so you just measure what is r, okay, what is r and what is z. So, once you know r and z at any location, so you find out, so you can find out the stress increase or the pressure increase by this expression. Okay. Now, the purpose of foundations. Okay. So, foundations means you know that every civil engineering structure is resting on some foundation base, right. So, foundation could be square, could be rectangular, you might have seen that in your say day to day life when some civil construction is going on, you might have seen some foundation is laid down in the soil. So, foundation, what is the purpose of the foundation? So, if you do not put the foundation, basically the column is resting on the soil, right. If you do not put the foundation base, that means the column is going to the soil. So, the column will try to give the concentrated load. The foundation, the function of the foundation is to distribute that load within a large area, so that the pressure increase or the pressure could be sustained by the soil itself. Okay, that is the idea. Okay. So, the purpose of foundations is to spread loads, so that point loads with the accompanying very high stresses at the contact point are avoided. Instead of foundation, if you directly put the column in the soil, what will happen? So, the load is coming on the column, which will be more or less acting as a concentrated load, and that concentrated load will be acting at a point on the soil. So, the stress concentration will be more at a certain point in the soil. The soil will not be able to take care of that high stress concentration. Okay. So, to distribute or to normalize that high stress, okay, over a large area, you generally put the foundation. Okay. So, though we are not talking about the foundation design and all in this particular course, because that is beyond the scope of this particular course. However, the foundation purpose is that. Okay. So, we can avoid this by considering. So, instead of this, suppose I mean if I put the concentrated load, okay, so I know what is the pressure increase, but generally we avoid that kind of situation by putting the foundation. So, once we put the foundation, we do not have any concentrated load, which is giving me the high stress concentration, okay, at the contact point. So, to avoid that situation, we are putting the foundation, and we can avoid this by considering the contact pressure Q naught to be applied to a circular area. So, we are considering one circular area over which some Q naught is acting. So, capital Q, that is the constant, that was the concentrated load earlier we have seen. The capital Q is uniformly distributed over a circular area, okay, with some stress intensity or the pressure intensity equal to say Q naught. That means, capital Q divided by the circular area is nothing but Q naught. So, if we have that, then basically we will be getting QV at any location below the circular loaded area will be obtained by this expression 7.3, where Q naught, as already we have discussed, Q naught is uniformly distributed load intensity, okay, on over the circular area, where R is the radius of the circle, okay, and Z is the depth at which you want to find out the stress. Okay. So, if you know R and Z, so basically you can find out QV, that is the pressure increase below the circular loaded area. Okay. So, this is also proposed by Boussinesq in 1885. So, all these methods are based on theory of elasticity. So, I am not talking about those complicated calculations or the complicated analysis, how to obtain this. This is not empirical. Please try to remember, these equations are not empirical, they can be derived based on theory of elasticity. Okay. Now, the equation 7.3 can be used to obtain the stress QV directly at depth Z for a round footing of radius r, as I told you. So, if you have the circular footing of radius r, you can find out the stress at depth Z, okay, by using this equation 7.3. Now, application to line loads. Suppose if you have the line load. So, line loads means you have a strip kind of load, okay. So, in one direction it is infinite, okay. So, suppose normal to the board is infinite. So, a continuous strip load, continuous line load. So, if you have that kind of loading, which is very common under the strip foundation or under the embankment, under the retaining wall, whatever is whatever plane strain condition you generally consider. So, below that you generally consider the line load. So, if we consider a vertical line load Q kilonewton per meter square of infinite length oriented parallel to the y axis, okay, then we get. So, y axis means if you see here, so y axis is here, right. So, parallel to y axis, if you have the line load, that means along the y axis it is almost infinite. So, if we consider a vertical line load Q kilonewton per meter square of infinite length oriented parallel to the y axis, okay, then we get QV, that is the pressure increase at any depth Z, is equal to 2 into Z cube into Q divided by pi into x square plus Z square to the power 2, okay, the whole square, right. So, where x and Z basically the distance, okay, along x axis and along z axis. So, if you have the line load along say y axis, so at any distance x and at any depth z, you can find out the pressure increase by this expression. Okay. So, if you know q, if you know x, that means location, that means x and z, so you can find out QV ultimately. Okay. So, this is the pressure increase happening in the soil at some depth z due to the line load. Now, if you have the square or rectangular loaded area, so instead of circular, if you have square and rectangular loaded area, then what will happen? So, Boussinesq has proposed equations for that also. So, applicable to square or rectangular bases, okay, this formula is applicable, this expression is applicable to the square or rectangular bases and round ones. Of course, the circular one can be considered converted, provided it is converted to equivalent squares. So, if you have the circular area, you can convert that thing with some equivalent square, right. So, and you know how to find out equivalent square. So, if this is R, okay, so the total area of the circular base will be equal to the area of the square base. Okay. So, based on that you can find out the side of the square, the side length of the I mean sides, okay, of that particular square. So, it is applicable to square or rectangular bases, and if you have the circular base, then you can convert that thing to the equivalent square base. Okay. Now, as per Newmark in 1935, stress beneath the corner of an area B into L. So, please remember, it will give you the stress at the corner of any corner. So, at any corner of the square or rectangular base, okay. So, this will give me the pressure increase. Please try to understand, it will not give me the pressure increase at any location within the square, rather it will give me the stress below the below the corner of the rectangular or square base. Okay. So, if it is rectangular base, then B is equal to L. If it is square, if it is rectangular base, then B is not equal to L, sorry. If it is square base, then B must be equal to L. Whatever may be the case, you will be getting the stress increase or the pressure increase at the below the corner of the loaded area. So, that QV, that is the load increase or the pressure increase, is equal to Q naught into 1 by 4 pi into this big expression, where footing size B into L and B is the shorter dimension or width. Okay. So, please try to remember, B is the shorter dimension or the width, M. So, in the previous expression we have got M, N, V and V1. So, M is nothing but B by Z normalized width, N is nothing but L by Z normalized length, normalized with respect to depth, and QV is equal to Q naught at Z equal to 0. So, you see you can match or you can get this thing from the previous expression. So, if your Z becomes 0, then basically you will be getting QV equal to Q naught. What is Q naught? Q naught is the pressure on the loaded area, that is the load intensity on the loaded area, and because of that Q naught you are going to find out QV at some depth Z, okay, which will be just below the corner of the rectangular or square loaded area. So, V is equal to M square plus N square plus N 1 and V1 is equal to Mn whole square. Okay. So, we have defined all those things. Now, when V1 is greater than V, then tan inverse term is coming negative. So, if you look at that expression, if you look at this expression, if V1 is greater than V, then what will happen? This tan inverse term will be becoming negative. So, in that situation basically what we do, so if V1 is greater than V, then tan inverse term is negative and it is necessary to add pi. Okay. So, the principal value. So, we consider the pi minus that. Okay. So, in general equation 7.5 can be written as, so whatever equation we have seen just now, equation 7.5, in general we can write equation 7.5 as QV equal to Q naught into I sigma, where I sigma is the stress influence value as given in table 7.1. So, we will see that. Okay. So, this is the stress influence value I sigma for M and N. So, along this you have M, along this you have N. So, for different values of, so whenever you are having, so the try to understand the process or the steps involved in calculation of this stress or the pressure increase. Suppose you have the loaded area B by L and you know the total pressure or the load intensity on the loaded area, say Q naught. So, if you know B and L, you can find out M and N. How? Already we have decided M is nothing but what? M is B by Z and N is L by Z. So, if you know B and L and which location you want to find out, that means at what depth you want to find out the pressure increase, that means if you know the Z, you can find out, or you will be knowing the magnitude of M and N. Once you know M and N, you can find out I sigma from this table. Okay? And once you know I sigma, from this expression equation 7.5a, you can find out QV. Very simple. Okay? Instead of going for different calculations and all those things from the equation 7.5, that will be very big equation, right. So, everything is done and everything is given in this table in terms of stress influence value. Okay. So, this is for m equal to 0.121 and n equal to 0.12 say 10. Similarly, this is for n equal to 0.1 to 10 and m equal to 1.1 to 10. Okay. So, for any value of m and n combination, okay, you will be getting the stress influence value I sigma, and once you know I sigma, you multiply I sigma with your Q naught, you will be getting QV, which is nothing but the pressure increase at just below the corner at some depth Z. Okay. I hope that you have understood that thing. So, now we are coming to the another method, that is Westergaard method. So, when the soil mass consists of layered strata of fine and coarse materials as beneath a road pavement or alternating layers of clay and sand, Westergaard equations give better estimate of the stress QV. Now, what does it mean? So, if you consider a layered strata, so far the Boussinesq theory is considering homogeneous soil medium, as we have decided homogeneous, isotropic, semi infinite, weightless, all those things should be there, then only you will be getting the Boussinesq solution. Now, if the soil is layered strata, that means you have, which is very common, right, you will not be getting very homogeneous kind of strata. So, if the soil is having layers, okay, just something like if you consider the road pavement, that means you have the base coats, sub base coats, widening coat, all those things will be coming, right. So, layer wise it will be laid down. So, at any depth, suppose due to the vehicle movement, what will be the stress increase at the base coats or the sub base coats? If you want to find out, then Westergaard method will be pretty applicable or pretty suitable. Okay. So, this will give you the better estimate for QV than the Boussinesq solution, because Boussinesq considers homogeneous strata, whereas Westergaard is good for layered strata. The Westergaard equations, unlike those of Boussinesq, include Poisson ratio. That is the biggest advantage of Westergaard method. Westergaard method considers Poisson ratio mu. That means, once you consider Poisson ratio, that means you are considering the lateral strain, right, or the that kind of, because Poisson ratio means because of this vertical application of stress, you will be getting some lateral contraction or expansion, right. So, that can be taken care of by this Westergaard method. So, that is the beauty, that is the basic difference between Westergaard and Boussinesq method. Now, as per Westergaard, for a point load Q, the QV, that is the pressure increase, can be obtained by this expression, where A, small a is nothing but 1 minus 2 mu by 2 minus 2 mu, where mu is the Poisson's ratio. Okay. This is the difference. So, if you know the location of that point R and Z, as I told you, I mean this is pretty similar, the diagram will be pretty similar than whatever we have seen for Boussinesq method. Okay. If you know R and Z, so you can find out QV provided you know the Poisson's ratio of the soil. So, that is the advantageous thing. So, layer wise and all those things you can calculate. As per Westergaard, under circular loading area, I mean like we are trying to map whatever we have learned for Boussinesq, the same thing from Westergaard, how we can find out. So, for under the circular loading area, that QV is equal to Q naught into 1 minus this root over A by A plus R by Z square, where A is nothing but same whatever we have seen in the previous expression 1 minus 2 mu by 2 minus 2 mu. The stresses for a rectangle of B into L can be obtained for the corner of the rectangular area. So, if I consider one rectangular area, just below the corner of the rectangular area we can find out QV as before, whatever we have done for Boussinesq, the same thing, same logic will be applicable here also, only thing is that the analysis procedure will be different. Okay. So, QV is given by this expression where A is already defined and M and N are defined earlier for Boussinesq and tan inverse is in radian. Okay. So, this tan inverse part is in radian. Now, M and N will be calculated or will be can be found out in a very similar way, right. What is M and N? M is nothing but B by Z and N is L by Z. So, those things will be remaining as it is, only thing is that tan inverse will be in radian. So, if you know M and N value, you can find out this QV. Okay. This is all about your stress in soil. So, as you have seen that how you can calculate the stresses, pressure increase at different level at different location below the ground surface due to some additional load on top of the soil, right. So, now we will take some numerical examples on retaining structure where you will be getting earth pressure theory, that means the lateral pressure, and we will be taking few numerical examples on the stress in soil. So, this with this basically your subject, that whole subject, that is geology and soil mechanics, that subject is concluded. Now, we will be taking few more numerical problems, so that you can understand whatever concept we have covered in earth pressure theory as well as stress in soil in separately. Okay. So, now we will take some numerical problem on earth pressure theory. Okay. So, the first numerical problem, that is your problem 25 in continuation with the previous problems. So, problem says a 6 meter high retaining wall is to support a soil with unit weight gamma equal to 17.4 kilonewton per meter cube, soil friction angle phi prime is equal to 26 degree and cohesion C prime is equal to 14.36 kilonewton per meter square. Determine the Rankine active force per unit length of the wall both before and after the tensile crack occurs and determine the line of action of the resultant after tension crack develops. Okay. So, this is the problem. The problem says a 6 meter high retaining wall is to support a soil with unit weight gamma is equal to 17.4 kilonewton per meter cube, soil friction angle phi prime is equal to 26 degree and coefficient C prime is equal to 14.36 kilonewton per meter square. Okay. So, these are all effective parameters. Okay. Determine the Rankine active force per unit length of the wall both before and after the tensile crack occurs. So, that means you know from the theory that in case of C phi soil, that is the cohesive soil, if you want to find out the active pressure, then basically you will be getting some tension which will be developed at the top part of the wall, and due to the tension you may get the tensile crack. So, you need to find out the active pressure before and after the tensile crack occurs and determine the line of action of the resultant after tension crack develops. Okay. So, that means first answer. So, for first our job will be to calculate the active earth pressure coefficient. So, phi prime is equal to 26 degree. For phi prime equal to 26 degree, your active earth pressure coefficient Ka is nothing but 1 minus sin phi prime by 1 plus sin phi prime, which gives me 0.39, and for our calculation we find out root over Ka is nothing but 0.625. Okay. So, it will be required later on. So, these things we have got at the initial stage. Now, active earth pressure Pa in case of cohesive soil, you know from this expression gamma z into Ka minus 2 C prime into root over Ka. Agreed? So, if you do not remember, please recall whatever we have covered when we talked about the active earth pressure distribution, okay, for cohesive soil. So, now at z equal to 0, what is your Pa prime? That means effective earth pressure earth pressure Pa prime is equal to minus 2 C prime into root over Ka, which gives me minus 17.95 kilonewton per meter square. Okay. So, 17.5 kilonewton per meter square. So, that negative sign is coming due to your tension developed at the top of the wall, which is pretty obvious, right. In case of active pressure, already we have seen that you will be getting tension which will be developed at the top of the wall. So, at z equal to 0, that means at top of the wall you are getting active earth pressure Pa prime is equal to minus 17.95, that means 17.95 kilonewton per meter square tension. Okay. Now, at z equal to 6 meter, that means at the bottom of the wall, what will be your active earth pressure? Pa prime is equal to gamma into h, that is the total height of the wall, into Ka minus 2 C prime into root over Ka. So, if I put all the values, I will be getting 22.77 kilonewton per meter square. Okay. So, that is at the bottom of the wall. So, if I have the wall like this is my say wall, this is your 6 meter. So, you are getting the pressure distribution like this. So, this is minus 17.95 kilonewton per meter square. What is this depth? This depth is nothing but Z naught, if you recall, okay, and this is your 22.77 kilonewton per meter square. Okay. Now, active force before the tensile crack appeared will be how much? Pa is equal to half gamma A square into Ka minus 2 C prime right. So, half gamma A square into Ka minus 2 C prime H into root over Ka, that means 0 to H Pa prime into dz, right. So, in that way basically you can find out capital Pa, that is the total active thrust, that is active force before the tensile crack appeared. Once the tensile crack appeared, then basically we have to consider, you have to consider only the bottom part, only the bottom part of the pressure distribution, because at that time once tension crack is developed, at that time this tension is not getting considered, already we have seen. Okay. So, if you put the values half into 17.4 into 6 square into 0.39 minus 2 into 14.36 into 6 into root over 0.39. Okay. From this I will get 14.46 kilonewton per meter. So, this is the first part of the problem, that means the active force before the tensile crack occurs, tensile crack happens. Okay. And active force after the tensile crack appeared will be how much? So, for that first you need to calculate Z naught. You have to see that what will be the portion which will be left out, right. So, Z naught has to be calculated. Z naught is, from our previous discussion, Z naught is equal to 2 C by gamma root over K. By putting all the values I will be getting 2.64 meter. Okay. So, therefore, your Pa, that is the total force, is equal to half into H minus Z naught. I hope you remember this expression, you just refer to your class note. Okay. So, from here I can write 6 minus 2.64 gamma 17.4 H is 6.39 minus 2 into 14.36 into root over 39. So, from this I will get 38.25 kilonewton per meter. Now, you just compare. So, before tension crack happens, you are getting this much of thrust on the wall, 14.46, right. Now, after tension crack happens, okay, you are getting the total thrust on the wall is 38.25. Why it has been increased? Because due to the tension crack, you are neglecting the tension of the top part, that means up to Z naught, whatever tension was getting developed, you are just neglecting. So, from Z equal to Z naught to Z equal to H, so whatever pressure distribution is there, that is the total compressive pressure is now coming to the picture. So, earlier case when the tension crack did not appear, at that time the tension from 0 to Z naught and the compression from Z naught to Z naught. So, this was nullifying each other. So, therefore, whatever was left out, that was here. That is why you are getting increase or enhancement in the active pressure on the wall after the tension crack happens. Okay? And it acts at Z bar, which is nothing but 6 minus 2.64 divided by 3. So, H minus Z naught by 3. Okay. So, at that location the point of application of this PA will be H minus Z naught by 3, which is equal to 1.12 meter from the bottom. Okay. So, I will stop here today. So, in the next class we will be solving few more numerical problems on the retaining wall, and then we will be solving few more problems on the stress distribution or the stress below the soil. Thank you very much.